Let's explore on spectral analysis methods of speech processing. The spectral analysis methods are used for front-end processing of speech signals and as a front-end system for the speech recognition system. There are many spectral analysis methods. They are as follows: filter bank model, the LPC linear predictive coding model, the vector quantization method. And there are basic steps involved in speech recognition like the parameter measurement, pattern comparison, and pattern testing. We see that in the signal processing techniques, we have to do parameter estimation in order to understand the pros and cons of every approach. And let's deal in detail about two important spectral processing approaches, namely the filter bank model and the LPC model. The filter bank model consists of bank of bandpass filters with specific quality factors, and each band pass filter is responsible for the segregation of a band of speech signal. We can see in this graph that the speech bands are overlapped so that we do not lose out even the small parts and segments of speech. The speech signal is passed through the bank of Q bandpass filters, and they have their own span of frequency range. The individual filters tend to be overlapping in frequency response so that we do not lose out any speech segment. The output of every bandpass filter is taken, normalized, and then plotted. We assume that the filters are independent to each other and the representation of every filter bank output is independently made. We see that the output of any LTI system is given by the convolution of the input and the impulse response. And so the output of the filter bank is taken as the convolution between the input speech signal and the impulse response of the bandpass filter. So we have Si of n as summation Hi of m into S of n minus m following the formula for convolution. And we see that the energy is measured and we tend this to be the band pass signal spectrum. Here we use a low pass filter to eliminate the high frequencies to overcome the aliasing effect caused due to the non-adherence of the Nyquist criterion. We have Q number of bandpass filters. We introduce this non-linearity in order to split the frequencies into its fundamental plus the harmonics. Then we bring out the low pass filter to take out the features and components that we require. And here is an interesting block called as a sampling rate reduction, in which we reduce the sampling rate as required. This will enhance multiple samples to be passed through the specific band. Finally, we come across the amplitude compression block, in which the amplitude is compressed using the Mulan-Alom algorithms, and finally we get the bands of speech signal for analysis. So filter bank analysis model is very interesting, very useful model for analyzing different segments of speech. So the output is taken as alpha I into sine of omega I of n, assuming that one pure sinusoid is in role. It is not so with the usual speech signal because speech is a composite signal and not a pure tone or a pure sinusoid signal. And here to elaborate on the purpose of a nonlinearity or the mathematical interpretation of nonlinearity, we take the output of a full wave rectifier. So we say that the output is Si of n when Si of n is greater than 0. It is minus Si of n when Si of n is less than 0. And now this windowing can be followed just in the place of Si of n. Wi or Vi of e power j omega is represented as the frequency domain equivalent of Vi of n, which helps us to find what is on the spectral or frequency domain of the speech signal. This brings us to Si of e power j omega into W of e power j omega. Since we see that there is convolution in the time domain, there is multiplication on the frequency domain. After nonlinearity, we lead the signal to low pass filter, then into sampling rate reduction and into amplitude compression. We can see the output in this graphical order. A pure sinusoid is taken, for instance, as Si of n. It is let into a window function, W of n. The output is the output of a full wave rectifier. And then we see on the frequency or the spectral domain side, we see spectral spikes at specific frequencies. So this is the typical analysis of speech signal using the filter bank model. Next is the Lpc model. The Lpc model helps us to predict and estimate the speech signals based upon the previous speech samples. So we split speech into blocks of frames. Then we make an Lpc spectral analysis, which helps us to do Lpc parameter conversion. Finally, we get the coefficients of the Lpc model, which are the representatives of the speech signal Si of n. And this Lpc model is nothing but a Hall pole filter model, which is the pth order polynomial that is followed by A of e power j omega, represented as A of z, given as 1 plus A1 z power minus 1, and so on. So our aim is to ultimately characterize and bring out the coefficients of the Lpc model. So how is Lpc used for speech recognition? This Lpc is used to make a good estimate of the speech signal. So it is an approximation of the vocal tract spectral envelope, and it helps us to differentiate the spectral envelope of one person from another person. So Lpc is way good in speech recognition and speaker verification. Lpc is very much used in the analysis of speech signals because it is helpful in vocal tract separation. And it is a tractable model because it can be analytically written down as specific set of mathematical equations, differentiation, and concluded as a matrix as well. And so Lpc is an analytically tractable model. Lpc works very well in speech recognition applications and also speaker verification applications because it is helpful enough to differentiate the vocal tract envelope of one person from another person. This is a typical Lpc model in which the vocal tract is emulated as an all-pole filter with gain G and source U of n. Please remember that the source of speech signal is the air from the lungs, and we take that as U of n. The air from the lungs, when they go through the vocal tract, they become pulses, quasi-periodic pulses, and that's why we represent them as U of n. The output is S of n. In Lpc, the current speech sample is given by the approximation of weighted sum of the previously estimated speech samples. And so we write comfortably equation 2 as S of n. The speech signal is equal to summation of AI, which is a coefficient or the weightage, into the previously available speech samples plus gain into U of n. So G is the gain of excitation and U of n is the normalized excitation from the lungs. Now taking Z transform of equation 2, we get X of Z is summation of ai s of z z bar minus I plus g into u of z following the z transform. Now boiling this down into a transfer function brings us to s of z by g into u of z. So h of z is equal to 1 by a of z. So the ultimate transfer function of the Lpc model is h of z is equal to a of z inverse. So this is the speed synthesis model based upon Lpc. So we take into consideration two generators, one as the impulse train generator that forces to give us voiced sounds like the vowels. The random noise generator gives us noisy samples or noisy signals which can be taken as a source for unvoiced speech signals. So the source can be either from the impulse train generator or from the random noise generator, and that becomes our u of n multiplied with the gain of the excitation g. When put into an all-pole filter or a digital time varying filter with all the vocal tract parameters put into it, we get the s of n. This is the speech synthesis model based upon the Lpc. Now for the analysis of Lpc, as discussed, S of n, the current sample is given by the weighted sum of the previous samples plus the gain of the excitation into the source of excitation U of n. Now to have an estimate, S cap of n, we take only the weighted sum of the previous speech samples and we estimate a prediction error based upon the difference of S of n to the S cap of n. So E of n is S of n minus the estimate S cap of n, and the error transfer function is given by E of z by S of z. Now A of z is nothing but 1 minus summation ak z bar minus k, and we go on to find the error and the speech segment of the adjacent samples. So how do we see that the error is minimized? We calculate the mean squared error and we try to minimize the mean squared error. So En is given by summation En square of m. Now this En has to be reduced, and so we differentiate En with respect to the Lpc coefficients and equate it to 0. So when we do this manipulation, we get Snm minus I Sn of m summation ak summation Sn of m minus I and another segment or a speed segment Sn of m minus k. To put this equation 9 in terms of covariance matrix, we can bring this down as pi of n, the available constants I and k, summation Sn m minus I, Sn m minus k. Since k is not available with this LHS, we bring this as pi n of I comma 0. Here pi n of I comma k is available. And we boil this down into a matrix format. Covariance matrix is followed here as pi n of 0 comma 0 summation ak cap pi n of 0 comma k for having a minimum mean squared error.